So good morning, everyone. Welcome back. It's so good to be with all of you on this Friday of the second week of COVID-19 spring 2020, talking about multivariable calculus. What a blessing it is to, in a time of separation, to be able to get together with all of you and talk about something that we all love, at least to some extent, that being mathematics. And do it in community at a time of such social distancing. All right, so when last we saw our intrepid heroes, they were understanding or learning how to find the centroid of a lamina. It's like a flat sheet that had non-uniform density. And so we did this first example where we found the centroid or center of mass of a triangular lamina. Today, my hope is that we can find the centroid in two additional examples. One, the first will also be a lamina, but it will no longer be able to use symmetry in quite the same way. So that will be somewhat interesting to us. And then the second is a three-dimensional example where we'll find the center of mass of a three-dimensional solid. And we're doing that primarily because it will allow us to understand how our formulas would look if we had triple integrals instead of double integrals. So that's our plan for today. I think we can just simply start with some crunching. So let me share the question with you, and then we'll start working this through by hand. Somewhere. Come on. Sorry, wrong section. All right, our question that we're going to start with is this example 2, and it says, consider a lamina that occupies the region bounded by the parabola x equals 1 minus y squared and the coordinate axes in the first quadrant, and then we're given the density function rho of xy equals y. We're trying to find the mass, and then later we're going to find the center of mass. So that's the question we're working on, and our process is going to be the same as we've had throughout the quarter, in that we're going to start by drawing a picture, and then we'll set up and evaluate various integrals and make sure we do our interpretation. All right, so here is the rough description of the question that we are working on. So we're in the first quadrant bounded by y equals 1 minus y squared, and we're given this density function. First thing we're going to do is always draw a picture. So this looks a little bit scary to us, but we recognize it could be a frowny parabola, but now it's sideways. So we have this sideways parabola with intercepts vertically at plus minus 1, horizontally at 1. And we are going to be focused on the first quadrant. So that would be just this region here. We have the choice of integrating this vertically or horizontally. And so what I would point out to you is that the equation is x equals 1 minus y squared. And so if we integrate horizontally, we will go in at x equals 0, and we will come out at x equals 1 minus y squared. So since the equation was already solved for x, we'll integrate dx, then dy. rather than dy than dx. All right, so let's set up a mass integral. This would be a massive integral, maybe. So step 2 is a mass integral. Okay. And so our mass is going to be the double integral over our region. We need to put in our density function, rho, which in this case I believe was just y. And we decided we're going to integrate dx, dy. Our x's are going to go from 0 to 1 minus y squared. And our y's will go from 0 to 1. This particular integral setup is really good to remember, because as soon as we have the mass integral set up properly, we can modify it pretty quickly to find our various moments of inertia. We'll see that in a couple of minutes, but so spending time to get a good integral to represent the mass is worth it, because it'll pay dividends later on in these centroid questions. So integral from 0 to 1 of yx from 0 to 1 minus y squared dy. Oh. So y times 1 minus y squared dy, y minus y cubed. So this is going to be 1/2 y squared minus 1 over 4 y to the 4th from 0 to 1, half minus a 4th or a 4th. What does this 1/4 represent?
Mass.
Mass, exactly, and that would be the mass of this region back here at the start. So we're saying this pink region has mass equal to 1 over 4.
And that's units squared?
It would be units of mass, so that would be kilograms. I guess it could be slugs if you were in the English system, something along those lines. Does that make sense? But it's a little bit of an odd thing to say, but as a mathematician, it's just sort of an integral. This is what it represents, and we'll leave it to the engineers and the physicists and the chemists to grind out the details of the units here.
Could you show the final derivation?
Yeah, of course. And of course, the derivations are always in my notes if you ever need them online.
Right. Okay, I got it. Thank you.
You got it? Good questions. All right. So the next step is going to be to find the moments of inertia. So the moments, not moments of inertia. So step 3, we need to find the moments. And so you're going to end up with a formula for mx, and you're going to end up with another one for my. Remind me, the moment about this mx would be the moment about the x-axis. And so in order to find the moment about the x-axis, we're going to need the distance from the x-axis, which is what?
Y bar?
it's going to require our, not y bar, that's what we're finding. It's going to require y itself. So recall this will require the distance from the x-axis, which is equal to y. And this one up here is going to recall, we'll need, so this is the moment about the y-axis. To find the moment about the y-axis, or the tendency to rotate around the y-axis, you will need the distance from the y-axis, which is x. So at this stage, we can go back to our previous question, our previous part where we set up our mass integral, and we can recopy that same integral in place, just leaving a little bit of space. And then we notice that what we need is the distance from the x-axis, or what we need is y. And so we can put in a y into this integrand representing the distance from that x-axis.
So there's two y's.
Yes, it'll be a y squared, exactly. And then down below, if we want the moment about the y-axis, again, we recopy that mass integral, exact same one as before. Sorry, yeah, that's right. And in order to find the moment about the y-axis, we need the distance about the y-axis, which is x. And so we'll multiply by, wait a second, I'm sorry.
Is this supposed to be y?
It is, I got a typo. X. Thank you, whoever provided that correction. Okay. Here's our formula for moment about the x, moment about the y.
So this is for center of mass, right?
That's what we're going for. In order to find the center of mass, we need, yes, we need the moments. Does that make sense? So these are like the intermediate steps to get there.
I was getting confused with centroid.
Ah, that's a good call. The center of mass is equal to the centroid. You might have heard this. Mathematicians we like to label things concisely. So center of mass is just way too many letters to write down. So we write centroid because it's just shorter.
Okay.
And it's cool. And sometimes what math is about is just being cool. That's not the only thing it's about. Okay. So we have set up these two double integrals, and at this stage, we just simply need to evaluate them. So let me switch over, and let's just look at that on the shared screen rather than running through a whole bunch of double integrals. So we found the mass of the lamina as 1/4. We already did that. Next, we need to find the center of mass. In order to find the center of mass, we need both of the moments. So the moment about the y-axis is that same integral, but now with an x. The moment about the x-axis is that same integral, but now with a y. And then you just sort of work through doing your normal integrations process. These are polynomials. You know, we all know how to do that. We all make mistakes because we lose track of a sign or a fraction or something along those lines. But it's a basic integration. And at the end of all those integrations, we discover that our moment about the y-axis is 1/12. My 1/12. And then we discover that our moment about the x-axis is 2/15. Okay. Here's the last bit it's not hard, but can sometimes trip people up. So remember that this moment about the x-axis here gets used to find y bar. So we take the moment about the x-axis, the 2/15, we divide by the mass.
Oh yes, I knew.
So here's your mix divided by m. And so it's a little bit strange, but you have the x here in the moment, but we're finding y bar, and that will find us the 8/15. If you remember the fact that the moment about the x-axis requires that you track how much y there is, I think that makes it a little bit easier. But I won't deny that the letters are a little bit confusing here. And then my is equal to 1/12. So there's the moment. We again divide by the mass. And that gives us our x bar of 1/3. And we put both of these values together. The 1/3 becomes our x coordinate of our centroid, and the 8/15 becomes the y coordinate of our centroid. And centroid is just code for center of mass. Questions about that? Let's go up and look at the picture. Make sure that it all lines up on the picture sense. So what we're saying is that our center of mass is at 1/3. I mean, this isn't to scale, but you get some idea. So it'd be at 1/3 in the x. And it'd be at 8/15. 8/15 is just over half, so maybe right here. I can do it. So we're saying that our centroid is this point right here. Now, you might not have calculated very many centroids in your life, but you probably have balanced things. Maybe a bowl of cereal going to the table or something along those lines. Does this look like the balance point of this region? Does that seem reasonable?
Yes.
Was that a no?
Assuming linear density.
Assuming what?
That your density is continuous.
So I mean, if you look at it, is there more area above the dot or below the dot?
Below.
There's more area below the dot. So if we put a balance point at this dot, at first glance you'd say there's no way it would balance at this point because there's more area here below, right?
Isn't the density changing though?
Exactly. It's exactly what I wanted to point out. It's a good call. So in this case, the density function is y, and so where is this thing going to be the densest? Where in this region? Where in this shape?
Wouldn't it be?
Yeah, at the top where the y values are biggest. So up here, it's dense you know, density equals what? I guess it'd be equal to 1, right at the peak. But down below, the density is 0, right at the base. And so it looks like the dot is shifted, is probably shifted up and left of the center of the region, and that's true. And the reason is because this is the densest stuff, and this is the least dense stuff. And so that's why the dot does not look like it's in the center of the region. It isn't in the center of the region. It's just in the center of mass. Does that make sense? Questions? Very good. Do you think that I'm not getting questions, but I also have done this long enough to know that some people probably aren't really happy with what's going on? Would people like to go into breakout groups for a few minutes and kind of talk through this process before we work on a more complicated thing? Are breakout groups good or bad? All right. Well, I appreciate your honesty. Let's keep going forward and see where it takes us. So what we've done so far is we found the centroid of two-dimensional lamina with non-uniform density. And now we want to find the centroid or center of mass of a three-dimensional object. So we need to sort of expand our knowledge into the three-dimensional world. So let's go back to our notes. And so imagine that we have a region here that's in 3 dimensions. And in order to find the centroid in 3 dimensions, we're going to again need the mass, which will require evaluating a triple integral. And then rather than talking about the tendency to rotate around an axis, now we'll talk about the tendency to rotate around a plane. So this MYZ is telling us something about the tendency of that object to rotate around the YZ plane. And so we would always be looking for what are the distances that we are from that YZ plane, and the distance from that YZ plane will be an X value. Or if we were looking for the moment about the XY plane, so this is the tendency to rotate around the XY plane, and in order to find that, we need the distance from the XY plane, which is here, and that distance from the XY plane would be the Z coordinate.
Does doing this in any other coordinate system make it easier?
A good question. The original setup will almost always have to take place in Cartesian, because we're talking about the tendency to rotate around a plane. But then when you go to evaluate the integral itself, you'll find that you oftentimes will want to use a different coordinate system. And I think we see that in the example that we're going to work on. So that's a good question. Did that answer it? So
Yes.
very good. So I hope from that you can see that this leads to the following formulas. These are analogs of our work in 2D. And so, do I not? Oh, there it is. So we have the mass itself is going to be equal to the triple integral across the region of the triple integral across the region of the density function dv. And then to find x bar, the x coordinate of the centroid, we'll take the moment about the yz plane and divide by the mass, which would be the same triple integral as before, but notice here we've added this x value into the integrand. And then to find y bar, we'll have the moment around the xz plane divided by the mass, which is 1 over the mass times the triple integral of same triple integral, but now we have y in our integrand. And to find z bar, same thing with z in our integrand. So you can again see that the most important integral to set up properly is that mass integral. As soon as you get that mass integral set up properly, you can easily modify that integral to find x bar, y bar, or z bar, or maybe I should say the moments about the various planes. Questions about those formulas?
So basically, we use these formulas to find the different bars for solid objects.
Mm-hmm. Yeah, for those of you that are both ADD and over 21, this is a good opportunity to do some safe bar hopping, right? You can go from the X bar to the Y bar to the Z bar.
Not yet then.
Yeah, but is you definitely can't do it at the moment because that would involve being socially close to people, and so I'm sorry, you got to do things safe. So,
man,
very good. All right, let me put you in breakout groups for a minute before we dive into the details, and let's see if there's any questions before we start throwing triple integrals around willy-nilly. So let me put you there for about 5 minutes, talk through the formulas, make sure people understand it, understand the process. I'll bring you back together again in a few. Let's go and look at one more example, but this time in 3 dimensions. So in our example, we're going to find the center of mass of the interior. Come on. Sorry, too many screens going. Center of mass of the interior of the hemisphere D with radius A with its base on the XY plane. The density is F of rho phi theta equal to 2 minus rho over A. That is, it's heavy near the center and light near the outer surface. And so if we want to find the center of mass, the first thing we need is our mass, and then we can go through and we can find our moments. So let's work through the mass calculation. So we've got a hemisphere with radius A and density function F equals 2 minus rho over A. It's a hemisphere, so any suggestions for a good coordinate system to work in?
Spherical.
Spherical, our friend. So M is going to be as follows. What's our density function is 2 minus rho over A. And then what is our scaling factor?
Rho squared sine.
Rho squared sine phi. And then this is going to be de rho to phi to theta. Where do your rhos range between?
Zero to A.
0 to A, because it's a hemisphere. Okay. Where do the phis range between?
2 pi, a full revolution.
So remember,
Should be 0 to pi over. pi over 2. Yeah.
Yeah, because remember that up here at the peak, this would be phi equals 0. And then we're rotating down.
Oh,
So
right.
this would be at phi equals pi over 2.
Right, thank you.
Thank you. 0 to pi over 2. And then our thetas, that's where we have the full revolution. So we'll go to 0 to 2 pi. Okay. So let's see. So 0 to 2 pi, just cleaning it up, 0 to pi over 2. And then we have 2 rho squared minus rho cubed over a, all times sine phi, de rho to phi to theta. We have a oh, I lost an integral. Clever. I can't fit it. Sorry, I lost the integral from 0 to a with respect to rho. So here's an important note to make in terms of integration. Are there any variables in the limits of integration?
No.
Not so much. And notice that in the integrand itself, we have a product. So we have a product here, no limits or no variables in our limits of integration. And so this means
So
we can use
separate out.
Exactly. We can use handy trick. So this is going to be the integral from 0 to 2 pi of 1 d theta times the integral from 0 to pi over 2 of sine phi d phi times integral from 0 to a of 2 rho squared minus rho cubed over a d rho. I went off the page. Okay. The integral from the integral from 0 to 2 pi of 1 would just be 2 pi. That's convenient. The integral from 0 to pi over 2 under sine phi, this is the area under half a bump of the sine curve, and that's just 1. This is like random fact that I know. This isn't like 1. And then the last part, we're going to end up with a 2/3 rho cubed minus rho to the 4th over 4a from 0 to a, 2 pi. Notice this is going to be 2/3 a cubed minus 1/4 a cubed 5/24.
You have a question.
Go ahead.
I was just looking at it. You had the integral of sine phi coming out as 1, but if we integrate it, we get, never mind. I see where I went wrong. Never mind.
Did it work?
Yeah, I dropped a sign.
Yeah, I had this is like a side note on this one. I had this math teacher back in grad school that he just, like, every now and then you get these teachers and they're like, their eyes would like get so big and they would get super excited about things. And he was one of those guys. And this one time I heard him go off for like 15 minutes about how crazy it was that the area under a whole bump of sine was 2 and how magical that was. And so because he was so crazy about that whole thing, I've never forgotten that particular random fact. So assuming I did my arithmetic right, there's a pi missing here. The mass is 5/24 a cubed times pi for our hemisphere. Are there questions? Go ahead.
It should be 10/12, right? That's 2 pi, not pi/2. So
Here?
no, your answer, the final one.
So
What
this
is-
is
12.
this is 8/12
Yeah.
minus 3/12,
That would
which
be
is
5.
5/12.
And you multiply by 2 pi, that would be 10, right?
Be 10/12 or 5/6. Is that correct?
Yes.
Yep.
Good call. Thank you, Twee and others, for keeping me honest. I get so excited about the things that I know that I forget to do my arithmetic right. So I appreciate having a team behind me. So 5/6 a cubed pi. Thank you for the assistance. Cool. All right, so let's talk through the last bit of process. This is finding the mass. If we wanted to find the moments, then we simply need to adapt the mass integral. So if we wanted to find the moment about, maybe it'd be let's try the xy plane, we would start with this same exact triple integral. 0 to 2 pi, 0 to pi/2, 0 to a, 2 minus rho over a, rho squared, sine phi, to rho, to phi, to theta. But then I have to add one more thing. If this is the moment about the xy plane,
Z.
I need a z, the distance from the xy plane, which would be a z. And this is going to be a little bit difficult to integrate as is, and so we have to recall that in spherical coordinates, that same z, sorry, 2 minutes, is equal to what? You guys remember this formula? What's the formula for z in spherical coordinates?
Is it equal square root of x squared plus y squared?
No, it starts with a rho.
Rho psi phi.
I think it's
Cosine.
rho cosine phi. Something like that.
Should be.
And then you substitute in the rho cosine phi for this z up above. If you wanted to find the moment about the xz plane, you have those same the same triple integral, 0 to 2 pi, 0 to pi/2, 0 to a, same integrand, 2 minus rho over a, rho squared, times sine phi to rho to phi to theta. But now we would multiply by what comes in here?
Y.
A y. Good. And we recall that y is equal to what? So think about polar. Think about what you'd use in polar. So it's in polar you'd have r sine. So in this case you'll have rho sine theta
sine phi.
sine phi. Okay. And then what would you do with each of these? So you could do the same thing for the last moment, but suppose we set that aside for the sake of time. if you wanted to use the mxy, what are you going to do with that mxy? You're going to divide it by
M.
m, and that's going to give you what thing at the end of the day?
Centroid.
It's just going to give you one coordinate of the centroid.
Z.
The z is going to give you z bar. And you could use mxz divided by the mass, and it would give you
Y
y
bar.
bar. And all three of them together will give you the centroid. So if you want to find the centroid, in this particular case though, just one note, what can you tell me about x bar and y bar in this particular instance?
They're all
They're
at the
equal.
order.
So x bar and y bar are going to be 0, like right through because of the density function and because of symmetry. The only one that's going to be of any interest to us is going to be the z bar. That's going to be the one we're going to have to work to find. So by symmetry. Woo.
The fun section.
It is. So this is a fun section. There's definitely some formulas to play with, which at first glance can seem a little bit intimidating, but the reality is they're all just sort of variants on the same thing. And all the work that we're doing in this class has been open book, open note, open friend. And so I don't think it's something that should be intimidating or scare you off. And so as we conclude this section, I think that you can see that the mass of all of our problems can really be nicely contained, can be easily understood and well balanced if we focus in on kind of the centroid of our or of their being. So thanks everyone. Have a wonderful weekend. And for those that are interested, I invite you to stick around and have a conversation about triple integrals and about math in the context of the COVID crisis and the mathematical modeling video that you watched. Thanks everyone. Have a wonderful weekend, and I will see you all on Monday.
Thanks, Dusty. See
Take
you.
care, Jay.
Take care.
Hey, Dusty.
Hey, what?
What was the mass of the half sphere?
Of the half sphere.
The one we just did.
I came up with 5/6 a cubed pi,
Oh.
which is different than I got on my notes.
What did you get on your notes?
On my notes, I forgot that it was a half sphere, and so that's, yeah, no, so I got 5/6. I got the same thing, I just didn't write it right on my notes.
Could I see the work again?
Yeah, of course.
Yeah, I got there. Oh, where did the 2 pi come from?
The 2 pi came from here.
Okay. Oh, okay. Yeah, I missed the 2 pi.
Very good.
Forgot to put in my limits.
Very good. Well, that's okay, because as I look back on my notes, I see that I made a mistake on the notes that I scanned. So we're human, and that's why we have teammates. So it's a good thing.
All right. Thank you, Dustin.
Take care.
You have a good weekend.
You as well. How are others doing? Do people have math questions, or you want to look a little bit at the COVID stuff and see where things have gone in the last week?